Right. Any will talk about the parabolic eigenvarieties, big parabolic eigenvarieties, and Iwasawa.
Well, thank you for the introduction, and thank you to all the organisers for the invitation to this, to what looks like it will be a lovely conference. So I'm here to speak about two topics which somehow I became interested in entirely separately. Parabolic eigenvarieties, Iwasawa theory. Somehow, parabolic eigenvarieties was what I did my thesis on, and shortly afterwards I was seduced into thinking about Iwasawa theory. It took quite a few years until I realized that there was actually a substantial overlap between these things. And thinking about Iwasawa theory leads to some quite interesting questions about eigenvarieties and their generalizations. So that's what I'd like to share with you here. So before I start, I'll apologize. This talk is going to be rather light on theorems and rather heavy on conjectures and philosophy. So maybe with the help of some people in the room, we can have some more actual theorems by the end of this week. I'll start with some familiar concepts from Iwasawa theory in the setting of modular forms. I'll take F modular form, some weight, some level, some character. P not dividing the level prime, and alpha root of the Hecker polynomial. And for some choice of embedding of the coefficient field into the p-adic numbers, I want to assume that the valuation of alpha is small relative to the weight. And then we can construct from this a p-adic L function. Remember not to stand there. Just to remind you what this means in a kind of eigenvarieties style language, weight space is going to be the homomorphisms ZP star to CP star, which is naturally the CP points of a rigid space. Theorem says that there exists, I should say this is a theorem due to Amis, Vishik, exists some LP of F alpha. It's an analytic function on W with some controlled growth property and an interpolation property at locally algebraic characters. So this guy is a function on the space of characters. I can evaluate it at a character x goes to x to the j times chi of x. Some correction factor times the appropriate critical value of a twist of the L function. So this doesn't uniquely define the p-adic L function. Each component of this guy looks like a disk, and we've just defined the value of the function at some countable family of points heading out towards the boundary, So this is heavily not dense, Zariski dense, and so it doesn't uniquely specify the compartments. And there are two ways of tightening up the characterizing property to make it unique. You can either remember that it has some growth property. I'll pass the function allowed to blow up as you go out towards the boundary of a component. Or you can bring in p-adic families, is after all why we're here this week. So result due to Kitagawa, Mesa, in the case of ordinary forms, and I think Stevens is probably the best person to ascribe this for. Ascribe this to for general families. For F Coleman family, eigenforms. Over some sufficiently small disk in weight space. There exists a two-variable L function, so let me just call it LP of big F. Which interpolates the critical values of the L function of all specializations, all classical specializations. So this is a function on some little disk in weight space, which is the weight variable, times the twist variable j. And when you specialize at k, you get back this guy for the weight k specialization of my family. And now this is obviously uniquely determined by the interpolating property. You even don't need these nasty finite order twists, just the values at the powers of the identity character are enough to determine this. Because the set of pairs k and j less than or equal to j less than or equal to k is dense in u times w. If you fix a k, then you only have finitely many j's, so this is clearly not dense in the one variable parameter space. But if you allow k to vary, then the set you get is manifestly dense. This product. So we have these nice two variable p-adic L functions. So that's one half of Iwasawa theory. Iwasawa theory generally sets out to relate something coming from L functions, some kind of p-adic L function, to something coming from Galois representations, a Selma group. So we expect this to be related. The Selma groups. Any questions so far? Yes, U is some sufficiently small neighborhood of a classical weight. So basically, because I want the map from the eigenvariety to weight space to be an isomorphism locally. So I pick some étale point in the neighborhood of that where I can invert the weight map.
Say that a countable set is not Zariski dense.
Some countable sets are Zariski dense, some are not. This one is not. because if you intersect it with any aphenoid, there's only finitely many points in the intersection. There's the log distribution, which vanishes at precisely all these points. So when I first started working in this area, coming up with the correct Selma groups to match up with these periodic L functions was a kind of weird and mysterious thing that people were a bit stuck on. So it's easy to define a Selma group for LP alpha of F, by which I mean one that looks like it should be, its size should be measured by that, if alpha is ordinary. And around about 2010, there were lots of groups, and I was a member of one of them, suggesting various approaches to this problem. Well, the approach that seems to have won out in the end was not mine. So this is an approach due to Potthast, which is to use triangulations of Galois representations. You look at the Galois representation of F restricted to decomposition group of P, if you consider its rubber ring phi gamma module, this is a rank 2 thing, and it has a rank 1 submodule E alpha, which comes from alpha as a root of the characteristic polynomial of Frobenius, which is this polynomial over here. And we use this as a local condition homology of D alpha define a Selma group, which is some submodule of H1. So essentially, you look at the cohomology classes, which locally, when you localize them at P, they land in the image of the cohomology of this submodule in the cohomology of the full representation, which you can calculate from its phi gamma. So this is Potthast's approach to defining Selma groups via triangulations. So this gives Selma groups corresponding to LP alpha of F, and they even vary over families of forms, because you can vary the triangulations for a family. This is the result of Kedelayer. So we have a robust setup for Iwasawa theory for families of modular forms. But of course, being able to formulate a conjecture is a long, long way from being able to prove it. And using Cato's Euler system, shows that the characteristic ideal, these Selma group, divides the p-adic function. Promote this to a two-variable divisibility as well if you want. And there are converse results. Due to 1 through k and so on, but I'm not sure if these are published yet. This is much more recent work. But in any case, there's enough is known to show that this is the right setup for Iwasawa theory for modular forms, both for one modular form and for a family. So before I move on to discussing more general kinds of automorphic forms and Galois representations, any questions on this brief survey of the GL2 over QP? Okay, not, then I'll proceed. So I'm going to put myself in a relatively straightforward setting of eigenvarieties. I'm going to take G over Q, reductive, such that G of R has a Shimura datum. But I'm going to allow zero-dimensional Shimura varieties, so I'm going to allow the case where G of R is compact. And I want G of QP to be quasi-split. So it should contain some Borel subgroup B. Of course, these needn't be defined over Q, they're just local at P. But I assume that at P I have this nice Borel subgroup. I'm wiping off white space, but it's going to reappear again in a few seconds. So I take an automorphic representation. E, say it's finite slope at P. If IP embeds in the principal series, so induced the character of the maximal torus induced up from Borel. So equivalently, if it's Jacquet module, Borel is not zero. So this allows any modular form of prime P level, or any modular form with a P in the level, as long as the UP eigenvalue is not zero. Lists of that, but you can't have something that's locally supercusped on P. This is somehow the most general notion you can have of finite slope for the Borel subgroup. And we define a P stabilization to be a choice of such a cup. And in general, there will be something like a Weyl group orbit of these if pi is unramified, or many possibilities. And there are many constructions of an eigenvariety. The concreteness, I'm going to use Eric Urban's construction. So this interpolates logical morphic representations. To finite slope. It comes with a map down to the weight space for G, which is equal to bonds from the ZP points of the maximal torus in my Borel, CP, and this guy is locally flat. The fibers are infinite in general, but each point of E, you can find a neighborhood that's finite flat over weight space. Over its image. So I'm sure you all know this at least as well as I do, or you wouldn't be here at a conference on eigenvarieties. And
You mean CP cross?
sorry?
You mean CP cross?
Yes, you are quite right.
And does one really know that it's locally finite flat?
In this situation where you have, this was why I assumed that G has a Shimura variety at infinity. So maybe I mean the components of it containing a discrete series automorphic representation of finite flat. And there's some grain of salt to do with the arithmetic subgroups of the center in cases like Hilbert modular groups. But yes, one should know this in this case. Is there a particular example you're concerned about?
Well, I'm just wondering how you prove that. I mean, I think I can see well that the spectral variety will be finite flat, but then it's usually harder to prove that the eigenvariety is finite flat.
I mean, like, don't exclude like Eisenstein series or some things here. So
I'm just working with the cuspal party. Okay, so maybe I mean the spectral variety is finite. It's finite flat, but certainly in cases like G compact and infinity, this thing really will be finite. At least it's equidimensional of the correct dimension. And the question I want to pose is this the natural home the Gal functions, Selma groups, Euler systems, etc. And the answer is going to be no. But I don't have I don't have a demonstrably better candidate in all cases. Sorry, I'm probably not. I should have gone for this one. No, I should have gone for it. And the reason that this seems to be the wrong question, wrong place to look for Iwasawa theory in families, is because you're fixing too much data. Fixing a P refinement and assuming finite slope is too much. So we should actually be looking for slightly less structure locally in P. For instance, Carte's Euler system is some family of Galois cohomology classes for a modular form. This just works without any finite slope conditions at all. And when you start looking beyond GL2, you see objects that need some kind of finite slope condition, which is more than nothing, but less than finite slope for the Borel. So if you look at Rankin-Selberg L functions, this is the L function that corresponds to the tensor product of the Galois representations of two modular forms. For there to be any critical values to interpolate, you need the weights to be different. If we take Kf to be the larger of the two weights, and to build the p-adic L function, you need F to be a finite slope. But not G. Whereas the finite slope condition that you see for the eigenvariety would be F and G both finite slope. So there's some discrepancy going on. And if you look at larger groups, then you find that somehow even less information is needed relative compared to the full finite slope condition we're at. This becomes much clearer if you look on the Galois side. Assume we know how to construct Galois representations, which we hope to be able to do in this generality at least. So to construct p-adic L functions, this is just with the S variable varying for now, or the things in bigger families later. We need rho pi p, or rather it's pi gamma module, to have a submodule, a specific rank.
Some representation of a dual group.
Yes, you're quite right. I mean, I need to fix a representation of the, I guess, of the C group into GLN, because in general, this Galois representation would land in some reductive group, and I want to regard it as a Galois representation as GLN by some choice of representation. So I want the recipe for how p-adic L functions should look, at least conjecturally, depends on a choice of a sub-representation of a specific rank, which is equal to the dimension of the plus eigenspace for complex conjugation. And this defines a Selma group with the somehow the right size. You cut the full cohomology down to something that you expect to be torsion over O of W. And if you ask about Euler systems instead, then you end up asking that there be a subrepresentation of exactly this rank plus 1. And now this explains all of these observations up here. So for GL2, for the p-adic L function, you need to have a rank 1 subrepresentation. So that's the trianguline condition. But for an Euler system, you need to have a rank 2 subrepresentation, which is just vacuous. You take the whole thing. And in the Rankin-Selberg case, to get a rank 2 subrepresentation of a tensor product, somehow take D alpha F tensor everything for G inside the rank 4 thing, D dagger ring. G. So having a triangulation of just one of the factors is enough to give you a submodule of this precisely correct size. And this is in contrast to being finite slope. In the sense above relative to the Borel subgroup, will give you a full flag of subspaces. And most of that data is irrelevant for the purposes of the target.
What about the Rankin-Selberg, like the Euler system that you constructed in a Rankin-Selberg case?
Oh yes, in the for the Rankin-Selberg Euler system, you need a rank 3 subrepresentation of tensor product. And the easiest way to do that is to look at the sum of this guy and the same thing the other way around. And the same thing with F and G reversed. And then you have 2 rank 2 subrepresentations with a common rank 1 intersection, and you get a rank 3. So yes, there is an Euler system in the Rankin-Selberg case, as Mladen is pointing out. And again, that's consistent with that picture. So for that Euler system, you need finite slope for both forms. Seems at first completely the opposite of what you see for Kato's Euler system, but it's actually consistent with this picture. Okay, so this suggests that maybe we want to take some kind of parameter space for automorphic representations with some different condition that is going to just give us the sizes of steps in the phi gamma module that we want. So, as I said at the beginning of this talk, I've begun my mathematical life thinking about certain eigenvarieties for parabolic subgroups. So I thought I knew the answer to this question when it came up in Iwasawa theory, but it's the wrong answer. And let me just describe that answer and why it's the wrong one. Now we don't assume that G of QP is quasi split. We just pick some parabolic. So we don't require it to be minimal or anything. And the whole group is an example. So this applies to any G, but it might give you nothing of any interest if the minimal parabolic subgroup in G is G itself, which can happen. So just pick any choice of parabolic. Here's a definition. We say I is finite slope for P, so P finite slope. If phi P embeds into the induction of some representation the levy of P. So this is going to give us on the Galois side representations that that fix partial flags in the phi gamma module. So maybe this is the right thing. But the way the theory is conventionally set up, we end up fixing a different set of data, which is again too much data. So here's a construction. Due to many people. David Morga worked out in the ordinary case. There's one of these things that seems to get reinvented repeatedly without reference to the previous work. So lots of essentially any construction of eigenvarieties for the Borel seems to be possible to adapt to the parabolic case. And lots of people seem to have done this without realizing that others had done similar things before. So it tends to get reinvented repeatedly. Anyway, so fix the following data. So we fix a G and a P as above, and we choose a little bit more stuff. Same level. Open compact in the finite Delta away from P. And we also choose a level for the semi-simple part of our levy, which is some open compact D in the derived subgroup of the levy of our chosen parabolic. And we should think of this as also being part of the tame level. We're sort of declaring this to be tame. We also choose an algebraic character of T intersect MP derived, where T is some choice of maximal torus. And then there exists an eigenvariety EP parameterizing automorphic forms, automorphic representations, P finite slope, and induced from some Tor. It's an MP representation
Here, who is T?
Sorry?
Who's T here?
Oh, T is some choice of maximal torus.
Sorry.
They're not quasi-split.
Not necessarily split.
An algebraic character.
Sorry?
Is it an algebraic character or?
Yes, that's what I added here. It's an algebraic character. So there's a condition locally at P, which is they're induced from some representation of the Levy with invariance under this subgroup of the derived subgroup of the Levy, such that the weight mu. So this is cohomological with weight mu, such that mu restricted to subtorus is equal to lambda. So this is a lot of baggage, but for example, in the case of Hilbert modular forms, P factors in your field as a product of primes P1 up to PR, we can fix levels some subset of the primes and not require finite slope at those. And we can in turn vary some components of the weight. So regarding the weight as a p-adic character, it splits up into components corresponding to embeddings factoring through each of these primes. And for the ones where we fix levels, we don't vary those components of the weight. We just vary this. So this is some sort of eigenvariety for a subset of the primes above P. This is the version that was treated by Yamagami a long time ago. I think this was the late 80s. And has been recently revisited by Chiyuan and Laden. Sorry? Yes, this was, maybe it was the 90s. I can't remember. It was certainly old when I was a PhD student. And this guy Yamagami was a student of Hida. It was it was not long after Hida's original work on families of Hilbert modular forms. This is very old. Maybe it was
In the ordinary case, he did it first.
Hida had done the ordinary case, and this guy Yamagami did something for non-ordinary families for definite quaternion algebras.
Before Coleman.
Yes, before Coleman.
A bit old, man.
I think I may have got the history wrong. It was before I started working in the area, so
It was more like 2005.
it's by Yamagami.
He's young. Younger than me.
Fair enough. I thought it was a long time. It was a fairly long time ago, and I think okay, I've got the history wrong, but but in terms of the development of eigenvarieties, it was still a long time ago.
David, I'm being a bit slow. What's D in the Hilbert case?
Sorry,
What would D be in it? What would the semi-simple level be in the Hilbert case?
So you're fixing. So in this case, the levy is just a product of some tori and some GL2s. So you're just fixing the level up to twists at the primes, at the subset of the primes you've chosen. So the extreme case of this, where you fix all the primes, you're just looking at families of character twists of a given eigenform, and then there's no finite slope condition at all. So there you're fixing a level for SL2. And yes, I am blurring some issues about L packets, etc., about which I'm aware that you are the expert. Anyway, I don't want to spend too long on this construction, because the point is that this is also going to be the wrong place for Iwasawa theory. The point is that as P gets further away from the Borel, so as P grows, this eigenvariety EP gets smaller. It sees more classical forms, but it varies them in less directions. The EP is up to minor complications coming from the center. It is equidimensional over a weight space 4p, so WP is equal to character space of the compact of the ZP points of the center of our levy. So as you make your group larger, or your parabolic larger, this torus gets smaller and smaller. So as I said, you're seeing smaller families. Whereas the hope was that this would somehow be the best possible place to do Iwasawa theory, seeing the most possible kinds of variation. So this is a bit of a disappointment.
I think the question is not too important, but kind of strictly speaking, is it actually the case that you see more forms because you fix more data and you fix this weight lambda or this character lambda, and it's like as the levy grows or the parabolic grows, the conditions on the weights then get stronger, right?
Right, but you're fixing something, but you can fix it to be whatever you like.
Sure. But I kind of, given the data you fixed, it doesn't really.
But the data is specific to P.
Okay, fair enough. Okay.
My point is that, for instance, for GL2, take a modular form that's where the local representation at P is supercuspidal.
Sure.
It shows up in this eigenvariety.
Sure.
All we do is put it in the family of its own character twists.
Right.
So we say something about it, but say something of rather less interest.
And then precise though, like Iwasawa theory in one variable is harder than in two variables.
There is merit in that viewpoint. I'm not sure that the statement is either entirely wrong or entirely right, but let me not try and answer it now. So maybe this is not the right way to go in my quest for the most general parameter space that you could do Iwasawa theory over. I should say that this has copious, fascinating applications to lots of other problems. So these kinds of particularly when we choose the situation so lambda is a non-regular weight. So I'm sure we'll be hearing much more about that from George later today. So if you want to do modularity lifting in non-regular weights, these parabolic eigenvarieties seem to be a very important tool. But for my immediate purpose of doing Iwasawa theory in as many directions as I can, they are the wrong. That's what it's for. So let's go back to the GL2 case again. This is now a new section. I'm now going to talk about another kind of parameter space for automorphic representations of DL2, which is in some sense much older than anything to do with eigenvarieties. So we're going to look at the setting of big R equals big T things. So I fix a tame level N. Consider Hecke algebra away from NP, so just the Hecke operators at the good primes. That's on all p-adic modular forms, tame level. No ordinarity over convergence, finite slope condition, anything like that. Just the biggest space we know about. So I let T equals this algebra. And its product of its localizations at maximal ideals. Maximal ideals correspond to mod P Galois representations. Well, and under some fairly mild hypotheses, we know that G rho bar isomorphic to R rho bar, the universal deformation rate. This is deformations of the mod P Galois representation rho bar with some limit on the primes that can ramify, N, but with no local condition at P at all. So this gives you a very large space, actually not too large. In the unobstructed case, when some Selma group associated to rho bar vanishes, which we expect to happen a lot of the time, this guy is isomorphic to power series ring in 3 variables. But these variables are non-canonical. They don't have any They don't have any kind of direct arithmetic meaning. They just come from choosing a basis of some Galois cohomology group, gives you a local parameters, and then lifting that. So we think of this as a three-dimensional polydisk, and we've got some parameter space substantially bigger than the eigenvariety, which in this case is two-dimensional, which is the largest possible parameter space for Galois representations coming from the bar. So we note the eigenvariety EL2. We're not fixing the determinant. So this is not the Coleman-Maser eigencurve. It's the product of the eigencurve and a product and a copy of weight space. I've just realized I completely forgot to say who this theorem is due to. This is due to Gebhard. Some extensions due to Emerton to push back the hypotheses on rho bar, but the original. And yeah, so the eigenvariety in this case is two-dimensional. Well, somehow a redundant dimension coming from the center that isn't doing anything very much. And you can think of this as embedding some very complicated curve inside some larger dimensional but much nicer space. And the fact that you can choose two different p refinements of a given modular form, give you different points on the eigenvariety, but the same point in the spectrum of this T rho bar, is saying that this thing branches an awful lot. It has this sort of fractal-like structure, and this is the infinite Fern. Uwe and Maser. The image of the eigenvariety in the space. So this has really extremely complicated geometry, but it's going on inside this larger space, which is really quite nice and smooth and well behaved. So, in danger of running out of time here. I'll give one very simple theorem showing that these kinds of universal deformation spaces are sometimes possibilities for parameter spaces for Iwasawa theory. If I take rho 1 bar, rho 2 bar, mod P. With these Galois representations. I'm going to assume rho 1 bar is ordinary at P. No such assumption on rho 2 bar. Two-dimensional. This is a Rankin-Selberg construction. Then there exists a p-adic L function on the four-dimensional space x rho 1 bar ord times x rho 2 bar, where this is the spectrum of the ordinary deformation ring. This interpolates Rankin-Selberg values. For all F lifting row 1 bar, ordinal, and G lifting row 2 bar with no condition at all. So the implication of this is that we should think of.
That's supposed to be an integral statement.
Sorry?
Is that supposed to be an integral statement, or are you the generic fiber?
We do get something integral, but to forestall awkward questions, let me just take the generic fiber for now. So I want us to think of this space as being something like a different kind of eigenvariety for the parabolic P is just the Borel in the first factor times the whole of the second factor in GL2 times GL2. And this one is bigger in dimension than the Borel eigenvariety. There is no, I'm not fixing anything like as much data. I'm not fixing somehow the semi-simple parts of the inducing representations. So the philosophy for a general P, we should have a small and a big P eigenvariety. The small one as in the previous section. But as you make the parabolic bigger, the small eigenvariety gets smaller, but the big parabolic eigenvariety is getting bigger. The universal definition space for a two-dimensional modular representation is the big eigenvariety for GL2 regarded as a parabolic set. Then obviously this is the at least the ordinary part of the corresponding eigenvariety for a GL for this half and half parabolic in GL2 times GL2. And it should parameterize Galois representations which have a filtration with blocks in and determined by P, but for the big eigenvariety, we don't fix the graded pieces. the twists, which we do for the small parabolic eigenvariety. So I'm running out of time, so I should stop there. But this is my yes for what the largest possible parameter space where you could do Iwasawa theory should be. Should be one of these big parabolic eigenvarieties. So thank you for listening.